your chances of attracting cutting-edge industry are diminished. We need to reduce barriers to the diffusion of these technologies, which I'll talk about in a moment, increase interoperability, so develop the standards so that the technologies can talk to each other. Issues of liability and transparency and ownership will have to be resolved. And some of these issues are new and evolving. So let me talk briefly about one to do with ownership. If you think now the relationship between a traditional industrial contractor and a supplier, say the contractor historically has wanted the supplier to provide it with a number of widgets, of inputs, which is subcontracting. Today, that situation is evolving because not only will the subcontractor have to manufacture the physical object which the contractor requires to maximize the efficiency possibilities of the entire digital system, the subcontractor will also have to provide what's called a digital twin. So with the physical item that the subcontractor is making, it will provide a digital file, which provides information on a whole range of performance parameters linked to that physical object that it's making, the widget, the input. Even parameters on the nature of the materials that it's made from, how those materials have been manufactured, and so on. And so a question arises, which we don't have a legal framework to deal with as yet, is who owns that digital file? Who owns those data? Can the contracting firm use those data itself to generate value? Can it sell those data to other firms that might be competitors of the subcontractor? So this is one of the evolving policy questions that needs to be wrestled with. And issues, of course, of digital security become ever more important when we have digital systems which are critical, and because they're becoming more pervasive, there are ever more potential points of entry for hackers. And there's an ongoing sort of war between the hackers and their targets. There may be technological solutions in part here, but they're always going to be short-lived. One of the most interesting I came across recently is developments in biomimetics, where the identity of the individual is actually continuously monitored by AI and is based on the frequency, the way you move your mouse, and the frequency with which you touch the keyboard keys. These have a fingerprint-like unique individual identifiers. It's not like a static identifier like a password or even a fingerprint. It's actually monitoring your use continuously as you're in the system from login to log out. It's a much more robust form of identity authentication. Anyway, moving on then to 3D printing, this is an area in which there's been a huge amount of innovation in recent years. So printers are getting smaller, they're getting faster, they're getting less expensive. It's now possible to print with over 500 different types of materials, to print objects that are composed of multiple materials simultaneously. You're not just printing from a single type of metal, for example. You might be able to print an object like a battery, which contains plastics and metals and other materials. Even possible to print with glass today. And with human cells, there are now 3D printers which will print down to the resolution of a single human cell. And this here is the first 3D printed motorbike. Now, in the book which we published, we focused on the implications of 3D printing for the environment. First, there's a question, though, about how pervasive, how widespread will 3D printing be in manufacturing. And it's important to point out that much machining work, so that's when you have like a piece of material on a lathe and you're cutting away from that material to bring it to a required shape. Much machining work is now replaced by 3D printing, so Boeing has replaced hundreds of machined parts with 3D equivalents. But machining overall is still a small part of manufacturing, more or less 5% in terms of value. And when you look at a stylized cost curve, you see this is the cost curve for 3D printing. And this is the cost curve as you increase the number of units, as you go to mass production. This is the cost curve, it's a very generic cost curve, for injection molding. So still today, the traditional mass production industrial technologies are more efficient than 3D printing at scale. But a key issue is that this line with innovation is gradually coming down. And two of the key factors which drive the cost of production using 3D printing are the speed of printing and how much energy is required for the printing process. And in fact, there's a company in California which has recently received a big venture capital investment, about $150 million, which has a 3D printer which prints thousands of times more rapidly than the current best sort of industry standards. So going back to the issue of the environmental consequences of 3D printing, well, some of these consequences could be benign, this could be positive in the sense that you can use more environmentally friendly materials to print shapes which could previously only be printed with plastics. So that's definitely a plus. It's also the case that some 3D printed parts can lower the environmental impacts of some products. So General Electric 3D prints nozzles in jet engines used by Boeing, and they lower the fuel consumption of the engine significantly, about 15%. We're thinking of a number of things governments can do here in terms of creating voluntary certification systems around the sustainability of the different printers, removing intellectual property barriers to enable 3D printing of repair parts for products that are no longer in production. And what I mean by that is, you think of your household goods, say a washing machine, that when the washing machine goes wrong, it might go wrong because a single component is broken. But as the washing machine is no longer manufactured, perhaps, you can't find that single component, so you put the whole machine into the waste stream. But what if you had something like an online database, a universal online database of spare parts that you could print from, and then you could diminish the introduction into the waste system of such no longer manufactured, such legacy items. There's work in Finland which is being done precisely in this connection, but there are intellectual property issues which would need to be resolved. So some royalty payments would need to be made to the owner of the intellectual property associated with the legacy product. Let's go on to industrial biotech, because the tools really exist today to begin a bio-based revolution in production. So bio-based batteries, artificial photosynthesis, microorganisms that produce biofuels are just some of the recent breakthroughs. Fascinating, at the start of last year, scientists in Australia were able to synthesize graphene on the right here, which is the strongest of all conceivable materials, 200 times stronger than steel, as electrically conductive as copper, which could itself have revolutionary impacts on the microelectronics, but has been hard to make at scale so far. But they've been able to synthesize this from, of all things, soybean oil. So if that's a process which again is scalable, that could itself have a major effect. So there's a range of public policy issues to deal with here. We need to make sure that we can avoid some of the dangers associated with garage biology. We don't want the ability to write strings of genetic code to fall into the hands of people who are just interested, for example, in increasing the pathogenicity of microbes. So we need to get the dubious customers out of the circle there. And notwithstanding the remarkable new biotechnologies that I just mentioned, the largest medium-term environmental impacts really in this area depend on the development of advanced biorefineries. So these refineries which will take everything from forest residues to agricultural waste to black bin, plastic black bin, liner, municipal waste, bung it all in and get energy and chemicals and materials from these. But these are, not all the technologies are completely proven. These are large, risky investments in biorefineries. The United States Department of Agriculture, at least under the Obama administration, was offering large loan guarantees, $150 million up to, for private investors who would go and invest in capacity in such biorefineries. And more needs to be done as well to develop interdisciplinary skills. And that's a sort of recurrent theme throughout this book, is that it's not just that we need more skills and more digital skills, but we need skills where, for example, in the area of synthetic biology and writing new genetic code, the experts know about chemistry, but they also know about biology and also know about programming and other disciplines. Nanotechnology, so it's the penultimate of the technologies we've been looking at. There's a great deal of hype around nanotechnology in the 1980s, and I think it's fair to say that quite a lot of that led to disappointment. There was an underestimation of the technical challenges of working at the nano scale. But we think that this nanotechnology will become ever more important, and there's two examples here of nanotechnological innovations. One, a product innovation on your left, and a process innovation on the right. And the product innovation there is a gold nanomesh. So just to give you an idea of the scale, a sort of nice graphic illustration is that the width, the thickness of a standard sheet of paper is about 100,000 nanometers. But each one of these holes, the pores in the gold nanomesh, is 175 nanometers across. That's 10,000 to 175. And you see how symmetrically and sort of uniformly manufactured they are. And this means if you put this nanomesh over a photovoltaic cell, over a solar cell, the light can get in, but it's hard to get out. And so the light runs around inside the cell, and you increase the efficiency of the photovoltaic cell. And on the right, this is where nanotechnology has allowed us to manufacture solar cells at ambient temperature, at room temperature, instead of with a very energy-intensive zone melting process used to date. However, it's in engineering and scientific terms, it's difficult to work at the nanotechnological scale. It's difficult to get all of the requisite instrumentation under a single roof of any particular institution. So governments need to work to foster inter-institutional and even international collaboration in this area. And there's also work to be done to ensure that we're not introducing into the environment nanoparticles that could have noxious long-term effects on health. Remember, these are not organic particles. They can get into the bloodstream, and the largest single user of nanoparticles in industry in France is L'Oreal, because the particles are used in lipstick. And another major user is in sun creams, and research in Australia off the coast has found large volumes of nanoparticles as a consequence of people going into the water, wearing sun creams, which then disperse the nanoparticles. So we need